Welcome back. We are continuing with the work done. Now we move to net work done. Work net. This one means almost three things. It can be net work done on an object, or it can be total work done on an object, or it can be work done by a net force. Work done by a net force. We just write net force, which is F net. Sorry for that. No problem. Then, therefore, work net in simple terms would be the combination of all forces that are doing work on the object. If I identify that there are two forces, I will always come back to this one. If you look at this one is doing work, this one is doing work. Therefore, the total work done on this object will be equals to the work done by applied force plus the work done by frictional force. This will be the total work done. And in this one, you can see that if I'm going to find the total work done, it will be now the net work done will be work done by applied force, which is this force, plus work done by friction, plus work done by Fg parallel. So very important to know which forces are doing work on the object. It will make this one very easy. Now when we continue, when we talk about energy, where now you now infuse the issue of energy, then we'll come to the so-called work energy theorem now. The moment we talk about energy and work, now there is what you call work energy theorem. Work energy theorem. Work energy theorem. Okay, let's unpack work energy theorem. The simple formula of work energy theorem says work net equals to delta EK. I always say this is for grade 12 because once there is friction, we have to use this one. Then work net, we have already said it can be which forces are doing work on that object. Let's say if we entertain that one, we'll be saying, according to this one, if you look at it, work net will be, let's say for diagram A, I will have now work done by applied force plus work done by friction equals to half mvf squared minus half mvi squared. This will be a very nice approach if you start this way. It will give you almost an impetus to get to the bottom of that one. Or in the second scenario of B, you will find that now you start, if they say use energy principles, you start with work net equals to delta EK. The next step will say now work done by applied force, plus work done by friction plus work done by Fg parallel equals to half mvf squared minus half mvi squared. This will give you very good approach to this question. That's when we fuse a work and energy. But if you go back to grade 10 said in the absence of friction, mechanical energy is conserved. Therefore, hence we had the principle of conservation of mechanical energy. Principle of conservation of mechanical energy. I hope grade 12s and learners and teachers, you know that mechanical energy is the sum of kinetic energy plus potential energy. So this gives us the mechanical energy. Therefore, between any 2 points, as long as there's no friction, mechanical energy will be conserved. Thank you. That is the grade 10 version of this one. We'll use it, or some people they use the grade 12 to say, oh fine, or what if instead of saying EM initial equals to EM final. Others, they use now delta EK plus delta EP give us 0. So whether you use this one or this one, both of them will give you the same answer, because the second one is coming to the conservative and non-conservative stuff. So that's the last point here, the second last point here before we go to power, to say work done by conservative forces, work done by conservative forces, or work done by non-conservative forces, conservative forces. Yes. Yeah, let's continue. Conservative forces. No problem. And then now, this is the formula. They say work done by conservative force. Let's start with conservative force. Conservative force. Force, which is the weight in this case. Work done by the weight. Work done by conservative force will be defined by negative delta EP. Or work done by conservative force becomes mgh cos theta. So you might choose which one you feel is good with you. And then work done by non-conservative forces. Conservative forces. This will be work done by non-conservative forces will give us delta EP plus delta EK. So this is the work done by non-conservative forces. I think up to so far we are fine. The last part of this section will be power. We know power is defined as the rate at which the energy is transferred. Energy is transferred, or the rate at which work is done in this case. Therefore, the very important formula of this one is when now we're calculating power average, which is your F multiplied by V average. Please be careful. V average equals to VI plus VF divided by 2, especially where now the motion, the velocity is not constant. If it's not constant, this is the case. But if it's constant, whether you do it this way, it will give you the same thing, because 10 plus 10 divided by 2 is 10. So that's why when it's constant, you don't have to do this. But when it's not constant, then you have to do this from where it started and to where it ended. That's in a nutshell, the work, energy, and power. Before we can deal with questions related to this section, let's just pause for now. Thanks a lot, and hopefully now you understand under which circumstances does work done, and under which circumstances work is not done, how to draw the free body diagram. People are saying in drawing free body diagram, first start with the weight. Either you start with the weight or its components, is okay. Then secondly, also you must know which forces in the free body diagram are doing work and which ones are not doing work. Please, we say draw the free body diagram even if you are not asked to draw, because it assists you in solving the problem. Thanks for now.